In this video, we're going to talk about initial value problems. So what an initial value problem is it's really an application of antiderivatives or integrals. So whenever we take an antiderivative, say we've found our antiderivative or we've evaluated the integral and we have our function. We remember how we always kind of add in that plus c at the end of integration problems? Well, what an initial value problem does for us is it gives us a value that our solution should satisfy. And so what that does is it gives us a value for x and y in our equation that we're going to find, in our antiderivative that we're going to have, such that by plugging in this x and y value, we'll actually get a value for our c. It will no longer be an arbitrary constant. We will determine what that constant will be such that when we put that plus c onto our antiderivative, it will satisfy the condition given here. Because what this condition is saying is that if we plug in the x value of -3, we should go through the y value of -3, say if we were to graph the antiderivative that we have given to us. So in order to do that, our c value has to be a specific number or a specific value. So we can use these two x and y values here and plug them into our antiderivative to figure out exactly what our plus c is going to be. So now that we've kind of laid out the format of how the initial value problem works and what it does, we got to figure out, okay, how do we do such a thing? Well, when we have a problem given to us in this notation, we recognize dy over dx as representing the derivative of y with respect to x, right? So, and what we also talked about, and this was a couple sections ago at this point, what we talked about is that these are differentials, right? dy and dx are individually differentials. So what we can do is, in a sense, we can multiply this dx to both sides. And when we do that, these divide away. So what we're left with is dy equals 6x minus 10 dx. So now what we see here is that we have all of our y terms on the left side, namely we just have like a constant 1 kind of floating in front of there, right, times dy with this differential of y. And then here we have equals 6x minus 10 times dx. So anything with an x, or anything that we can integrate with respect to x, is on the right side. So what we've done is, this is a branch of mathematics that kind of gets started with differential equations. It's kind of one of the very first steps into looking at differential equations, but this is what is called a separable differential equation. And it's specifically a separable ordinary differential equation. And what this tells us is that if we get all of our terms that have a y on one side of the equation and all of our terms with an x on that other side of the equation, we can integrate both sides individually with respect to the variable that we're integrating with, and we can give ourselves a solution y in terms of x of this problem. So it'll return to us a function in terms of this variable x over here that we have, and that in such a way that we can use the initial value condition that we have given to us in this problem. So what we're going to do is we're going to try to find the antiderivative of the constant 1 with respect to y, but we're also going to find the derivative of the equation 6x minus 10 with respect to x. So let's go ahead and do just that. Well, the integral of a constant like this, what that's going to give us, we can use the power rule in a sense, because if we have 1 times y to the 0, that all evaluates to just 1, right? So by using the power rule, we know that we add 1 to the power and divide it by that power. So the integral of 1 dy, or the integral of just dy in this case, will just give us y. And we know that there's kind of understood to be this plus c here, right, in terms of what we have going on here. But like we said, since doing all these operations of moving the plus c around and multiplying by everything like that, we'll keep it here for right now, but we will talk about why this plus c can kind of be left to the end when we talk about these problems in the future. So we've integrated the left side with respect to y. Let's integrate the right side with respect to x. So here what we have is the integral of 6x minus 10 with respect to x. So here we're going to use the power rule again. So our original power here for this 6x is 1. So let's add 1 to that. So we get 6x squared over 2, right? Because if we increment the power, we still have to add 1 to it and then divide, or incrementing the power is adding 1 to it. What I meant was, after we increment the power, we have to divide our new expression that we have by that new power, okay? And then so similarly, what we're going to have is, since this doesn't have an exponent power, it's like x to the 0. Once we increment it, what we're going to get is just 10x, right? So we have minus 10x. And then again, after we integrate, we have a plus c, this arbitrary constant that, if we were to differentiate this, would still give us this thing, but this arbitrary constant counts for the fact that what if there was a constant tagged on to this function? If it was just this would give us 6x minus 10, but this plus c accounts for the fact that if we were deriving this function, it had like a 3, a 16, a negative 4, something like that tied to it. That would evaluate to 0, but we need to incorporate it inside of this plus c. That's why we have it there. And so if we want to get y by itself on this side of the equation, be able to use what we have going on here, we're going to essentially move this arbitrary constant that we had on the left side to the right side. But what happens when we have an arbitrary constant, we subtract an arbitrary constant? Well, what's going to happen is not that they cancel out, but by the nature of what we did over here, the exact value of this arbitrary constant, we moved it to the other side, so we know that this cancels out and goes away by the additive inverse property, so we're left with just y. And then here we're going to have this 3x squared minus 10x. But there's no guarantee that this constant has the exact same value as this one. So in that case, this plus c is still going to be, and I can notate that better. Let's call that C1 and this C2. So we have C1, C2. So there's no guarantee that C2 has the exact value as C1, right? So what this will give us is some new arbitrary constant that will still be an arbitrary constant. So what we're still going to keep that as is still a plus c. So combining C2 and C1, since we only have one plus c now, we're going to think about this as just itself, as a plus c that we're going to need to solve for. And the reason why I say that is because the initial value condition that we're given here is going to be used to solve for this plus c. Okay? So now that we have what we believe to be our antiderivative, and by doing a quick little differentiation of the power rule inside of our head, we see that the derivative of this does give us this, so we're all good there. So we know that this function y equals 3x squared minus 10x plus c is the general antiderivative of this, but now we're going to use the initial value condition to figure out what the exact antiderivative of this function is that satisfies this condition. So what we're going to have is we have negative 3 equals 3 times negative 3 squared minus 10 times negative 3 plus c. The reason why we leave plus c as a plus c is because we're solving for it, right? We have a value for x and we have a value for y, so we went ahead and plugged those values in where we saw x's and y's, and now we're going to solve for c. So here we get negative 3 equals 3 times 9, it's 27, and then we get plus 30 plus c, so we get negative 3 equals 57 plus c, or c equals negative 60. So now that we've found the c value that allows our antiderivative to satisfy this initial value condition, we're going to plug this back into our general antiderivative to give us the specific antiderivative for this initial value, thus solving the initial value problem. So we get y equals 3x squared minus 10x minus 60. So what this means is that this solution that we have here, this quadratic that we have, if we were to graph it and look at it on a graph, it would satisfy this condition. It would go through the point negative 3, negative 3. Okay? So that's what we're talking about when we talk about initial value conditions, is it's giving us a condition that the function, that the antiderivative must satisfy. So essentially what we end up doing is we end up solving for c because of this initial value condition. So we talked through a lot of stuff inside of this problem, and it's kind of a lot to think about and a lot to try to handle, but in a sense, when we have dy over dx, we can treat this as a separable equation and deal with the integrals with respect to y and respect to x separately. It's why it's called a separable ODE in that branch of mathematics, a separable differential equation, because we're going to end up taking the antiderivative of each side with respect to the variables individually. And then what we're going to end up doing is, after we find a general antiderivative for something that looks like this, we're going to use the initial value condition to figure out what our specific value c is, such that the antiderivative satisfies this condition.